assume that something's, like that class is canceled. If I'm not here in like 10 minutes or something, and I haven't put out an announcement, just go home. Send me an email. I don't know. I'll be fine. It's just life. Okay. Let me present this. How the hell do I present? There we go. What? There we go. Okay. So I guess I'll start talking about isomorphisms, because I love isomorphisms. If there's one thing that I want you to know about me, it's that I love isomorphisms. So an isomorphism is a function. It's a special kind of function. So if we say T is an isomorphism, right? That means two things. And it pretty much always means these two things. Whenever you see the word isomorphism, even if it's in a different class, if it's in a different context, it always means these two things. Number one, homomorphic. And two is bijection or bijective. So a function is an isomorphism if it is homomorphic and it's bijective. And maybe you're wondering, what the hell do those two mean? In this course, homomorphic is the same thing as linear. So a reminder, linear was like, it has to be additive and it has to be homogeneous, so you can pull out like a constant. In other courses, it may not be exactly this, but the general idea is that like it's still going to be this idea of homomorphism or homomorphic function. Yeah, and so why do we say homomorphic? Where does that word come from? Homo means similar in Greek. Morph means shape, so it's, or structure, so it's like similar structure. Isomorphic, iso means equal, and morphic means structure. So isomorphism means equal structure. So if you have these 2 points in linear algebra, at least if you have these 2 points, then we say that the function's linear, which is the exact same thing as saying that it's homomorphic. Those two words are equivalent in this case. So we found a homomorphism. That means that the two vector spaces, so if T runs from U to V, that means that U and V have a similar structure. Maybe not exactly the same, but they have a similar structure if you can find some homomorphism or some linear transformation. The second piece here is bijective. So a function is bijective if it is injective and surjective. And injective is the same thing as one-to-one. It's always the same thing as one-to-one, and surjective is always the same thing as onto. So we talked about that a bit last time. Yeah, so if you have a function that is homomorphic and it's bijective, then it's an isomorphism. Or phrased a different way, if you have a function that is linear and is bijective, then it's an isomorphism, right? Why is isomorphism interesting? The reason isomorphism is interesting is because say that we're like starting in U, we want to do like some operation of things inside of U, right? Maybe U is some really bizarre vector space, right? There are like lots of really weird vector spaces, right? But, you know, a common vector space that everybody sort of probably knows how to work with is like Rn, right? Or like real numbers to the power of n, right? Real vectors. So what we can do is we can use isomorphism to go from U and translate the problem that we have in these weird vectors into a problem in like easy vectors, like V, right? Or maybe these are like, maybe this is like R. It doesn't have to be, but you translate it into something that's like Rn maybe. You translate a problem that's maybe it's in matrices, maybe it's in polynomials, something weird, and you turn it into a problem with just Rn, like just n-dimensional vectors. And from linear algebra, you know how to deal with n-dimensional vectors, right? So you can do your work. So do your work and get your answer using, in this case, Rn, but it doesn't have to be, right? It can be anything. You do your work, and then you translate the problem back to U. Does that kind of make sense? So if we start with something, a hard problem to solve, we can turn it into an easier problem to solve in like a different vector space, solve it in that easier vector space, and then turn it back into the original vector space and get our answer, right? Does that kind of make sense? So like as an example, you know, like I think we talked about dot products of weird matrices. So like if I said like the inner product of A with B, if A and B are matrices, I think I told you that was the trace of B conjugate, I guess, A, or B transpose A, depending on what kind of matrices you're working with. But that's hard to work with, right? Like this is not a standard thing, right? But if we turn these matrices into vectors, then we know how to do dot products with vectors. Those are easy, right? Just multiply each entry. And so then you can turn it back to U and have your answer without having to do any crazy math. Does that make sense? I think that's basically all I wanted to say about this. Any questions about homomorphisms? Or isomorphisms, I should say. Now, if you can find an isomorphism between U and V, there's sort of two ways to write this. One way is to write T maps U to V and to put a little squiggle above it. That squiggle means that T is an isomorphism. The other way you can write it is that U is isomorphic to V. So it's like an equal sign, but the top line is like a squiggle. It means same shape. Not exactly equal, they're not the same thing, right? But they're similar. All right, with that said, I'm going to stop this recording, which I never started. Oops. Oh no, I did start it. Good. How do I stop it? Stop. Great.